Alrighty then. The thing has gone red, so it means we must be on. Hey guys, what's going on? Memes here. Yes, yes. You all may have seen a few headlines going around over the past week or so. It's like, do we live inside a black hole? Short answer, I don't know. A lot of folks are like, no, no, no. But where the heck are we getting these headlines and everything from? So I see we have a few folks that have already rolled through, some folks that may be temporarily joining us from across the internet, whether it's the YouTubes, the Twitters, the Blue Skies, all the other places I occasionally post or forget to post links and everything now. So we've got David. Yes, yes, howdy everybody, as well as we have the mad scientist himself, Mr. Rick DeWitt. Yes, good to see you, my friend. All right. So where the heck is this stuff coming from? Because if you've been around on the internet for a little while, yeah, you've probably come across, I don't know, maybe something like this with the title. It's like, "Do we live inside a black hole?" You, you may be wondering about the wolf-like creature in there. Apparently, I've hung around with Fizz for so long that even within like a new chat GPT chat, I literally asked, it's like, please make me a 16 by 9 picture of a black hole. That was it. This is what it created. The spirit of Fizz is with me no matter what. I had to do it without it, but it still had the swirl, and at least the wolf looks kind of cooler. So I thought it was endearing. All right. So where are we getting this stuff from? All right. So let's quit out of that. Boom. All right. So where was that? Oh, we have the article over here. Okay. So basically the whole James Webb Space Telescope, that thing where there'll be some data released and then you'll see a lot of clickbaity videos. It's like JWST destroys modern cosmology or does this or does that. It's like it's raising a lot of interesting questions. So now what I would say is, and again, I'm just a dude on the internet. Take whatever I say with an entire ocean of salt. Um, there are some folks out there, and it's kind of popular to be anti whatever a thing is or pro whatever a thing is. That's totally fine. You do you, boo. For me, I look at it, I'm like, all right, well, some folks are taking a really extreme position. And then if somebody happens to have their career revolving around a particular thing, and there may be some evidence that maybe is making the foundation or some of the surrounding area a little bit shaky, it's like, well, why wouldn't somebody defend that? I mean, that's just kind of in their own best interest as well. And again, there's varying degrees around all this. What I'm looking at is what's actually going on. All right. So, in order to find out what's actually going on, let's actually go to what the heck we're talking about. Oh, we got Maria. We've got Maria. Hail Maria. From Unlocking the Lore. If you like stories and different artwork, and especially dragons, feel free to check out Maria's channel on there. I'm sorry I didn't make it the other day. I'm going to be traveling again. I may pop in the greater Toronto area beginning of June-ish. So just putting that out there. Roar! Yes. Yes. Release the dragon. That's what I've been saying for all the folks trying to get the Capcom to remake Breath of Fire and stuff. It's hey. I'm not saying okay, if you look at back at some of the original games, that may or may not be literally why I'm doing. I say anime hair because people get that, but it's kind of JRPG hair. Really, really. I just got my passport expired. I was planning on going back. I had to have a new engine put in my car. Long story. Yada yada. Bada boom. Bada bing. My passport had expired, and I'm going to Portugal in June. So I literally was down at the post office today. Have all the things, new copy of your birth, blah blah blah, all this status, submit it, expedite it so I can get the passport book. Hold on. Okay, I should have my mail forwarded then, because otherwise I can't really drive back if it's okay. Thank you, Maria. You helped me plan again. Okay, black holes. What the heck are we talking about here? Okay, black hole. What is a black hole? It's basically when you try to cram a whole bunch of mass or energy in too small a place and everything, and then it just magically creates what we believe is a black hole. Now, people would disagree with that. There's all different science and stuff and all these calculations you can do. All right. But why the heck are people saying that we live in a black? Oh, I am on the right page. Okay. Sorry. The modern web. Maybe this is why Jack Dorsey was tweeting earlier. Repeal all IP laws or whatever. All right. So let's go over here. All right. A puzzling observation. This is, of course, you do the quick search for the Royal Astronomical Letters and it gives you a phys.org article because, well, of course you can advertise. All right, the link's in the doobly-doo. All right, puzzling observation by JWST. Galaxies in the deep universe rotate in the same direction. Okay. How do we go from this to we live in a black hole? Let's continue a bit with the article here because it'll start making more sense, and then we'll go into some very light mathish stuff, basic calculations that it'll just show. We'll just get into it. All right, in just over 3 years since its launch, NASA's James Webb Space Telescope, JWST, has generated significant and unprecedented insights into the far reaches of space. And a new study by Kansas State University researcher provides one of the simplest and most puzzling observations of the deep universe yet. In an image of the deep universe taken by, yep. Oh, this is the JADE survey. Because they can JADES. It sounds cool. All right. The vast majority of the galaxies rotate in the same direction, according to research by Lior Shamir, an associate professor of computer science at the Carl R. Ice College of Engineering. About 2/3 of the galaxies rotate clockwise, while just about 1/3 of the galaxies rotate counterclockwise. All right. Here's the link. There we go. See, I just actually needed to read deeper into the article. There we go. All right. So how do we go from this? How do we go from this? All right, let's get out here. So let's see. Hex. See, the interesting thing is for me, it's like I remember when I heard that, like kind of as a kid about black holes and stuff. It's like it just gets crushed down so fast, and it's infinitely small. For me, I'm just like, well, since I didn't know any better, I'm just like, all right, if you're gonna take a sphere, you know, they crush down this ball-like thing. I just thought you would just keep going. It would just invert itself, or do. I probably didn't know the word invert or something at that time, but I'd seen what an asymptote is. What the heck is an asymptote? An asymptote is just that line where, whenever you know, in math class where you have this your little XY Cartesian thing, it's that thing that goes. So it almost crosses the line, but it gets infinitely smaller, and then almost crosses the line, but it never quite touches. That was an asymptote. And that's probably one of the few things I actually remember from math that I'm like, all right, there's a limit there. I don't know what it is, but there's a limit at some point. The interesting part, I tend to be very, I don't know about black holes. Well, then again, to be fair, one could claim that if we did live inside a black hole, that might explain a lot. In that, number one, as far as that singularity, there is a little bit of a workaround for that, so to speak, if you want to take a particular geometry, aka the hyperbolic figure 8 knots complement, into play there, because what it does is it does have a central point that's literally characterized mathematically by the 0, 0, 0, 0 point. I don't know about you guys. I'm not a professional geometer, but that sounds like 4 zeros. Maybe that's like a 4-dimensional point where everything just kind of goes around it smoothly. Or I did a stream, I think either earlier this week or last week, where it was not the singularities you're looking for, something like that, where it's literally the cheapest excuse. It's like, all right, for Planck length, there's a minimal length. You do a Planck mass black hole into the equations and everything. It's like, Well, to be fair, for every Planck mass, which is effective 1, the radius goes up by 2. Why? Let's get back into the whole thing there. All right. Rotating. Oh, hey, we got Greg. Welcome, Greg. Greetings, my friend. Uh, see, that's the thing. I'm going back and forth on black holes. My initial thought is it's just a whole bunch of mass. We're just getting it together there. Simplest explanation. I don't know. I don't know. But why are people saying that our quote unquote universe? And again, if I'm using universe, unless otherwise stated, I'm using lower u. Why? Because I'm a crazy person and I happen to think if the Planck length is the minimum length, there's a maximum extendability to that, which would be its inverse in meters, which is like, it's ginormous. It's like 100 million times larger than the observable universe. But there's a limit, which then raises the what's outside? That's an ill-posed question. I don't know if we're saying it's in a black, if we might be in a black hole, there might be some, there be dragons, turtles. I don't know. I think, wait a second, we actually have media for this because, well, I mean.
Do you like turtles?
Is it a crazy thing that I started listening to like the Wolfram live streams and everything? And I kind of went initially just as a troll, just to see if I could maybe get Stephen Wolfram into the position where he could say something
world
like,
exists on the top of a giant turtle.
I mean, that's how I started out, mostly just doing silly clips and stuff of folks. And then today, what is it? I asked him a question about 4-dimensional platonic solids. And then he went into a 20-minute spiel about that 4-dimensional platonic solids and how they could be applied to error correction. I'm like, I didn't even think about that. So we just posted that a little earlier. You know, got to check out my videos. Feel free to just check out his live streams. It's an interesting train of thought. Well, this is the thing. All right. So let's go over this, Maria. So the whole claim about why was I showing you this? Okay, if more galaxies are rotating in one direction, big hoot. Who cares? The thought process is, all right, so as far as we know, and we could be wrong here, when you get a star and it goes through its lifespan and everything, it spans really big to like a red giant phase, and then eventually it kind of like runs out of juice and everything, and it can no longer emit enough radiation to keep up with gravity. So at that point, gravity starts to collapse. When it comes in, it condenses, and you tend to have some form of a supernova, as we know it. That big super flash that can outshine entire galaxies. A lot of energy being emitted. Okay. Now, the thing is, as far as we know, most everything seems to kind of rotate. All right. The Earth, as far as we know, the Earth seems to rotate around the sun seems to be rotating. So the claim is that when you have a star that's reaching the end of its lifetime and it ends up collapsing, remember, the stars are spinning. So the thought process is if you have that angular momentum, that rotation, as the star is collapsing and it becomes a black hole, that angular momentum would be transferred to whatever ends up coming out. So hypothetically, if we lived inside a black hole, you could think of it kind of like you're getting this star spinning, supermassive star spinning around. It runs out of juice. All of a sudden, it can't fight gravity anymore. It doesn't have enough juice left via fusion to be able to push out on that pressure. Gravity wins. It becomes a black hole. And as far as we've observed, objects that we believe to be black holes, which personally, I think we should actually rename them mass holes because, well, they're not black. They're technically invisible to a lot of the light and stuff unless it's emitting something. I'm also biased. I'm a mass hole born and raised. I also think I think it would lead to maybe more giggles. Personal opinion there. Hey, it's okay. It's okay. I like both those. I think actually my YouTube channel does say something like I like dragons, money, and turtles, or something like that. Well, how come light bends if it has no mass? That's a very interesting question. It's the claim is the space-time medium, whether you want to view it as the fabric of reality, some type of superfluidic thing, totally not the ether. Why? Because that's a 5-letter word. It gives people the creeps. Since it gives a lot of really smart people the creeps, that may be, to be fair, Einstein, the generalized story is, oh, when he did general relativity, he's like, we don't need an ether or anything like that. And a lot of people are like, cool. And then later, Einstein, apparently, he was like, okay, so to be fair, that doesn't mean there can't be an ether. Like having some form of a medium actually might make sense. Or again, please go to an actual physics historian or something, because they would know better than me. Oh, that's interesting. Welcome, Kali. Kali is stating that there is no such thing as a direction of rotation to an object in free space. It is dependent upon the observer location. I need to try to parse that, because my thought is, it's like, all right, what level of analysis do we want to go? Because if I was the Earth, as far as I know, I would probably be turning or something. Oh, then again, no, that's a great question. I'm gonna have to come back to that. Yes. Yeah. As far as I understand, Rick is correct. Light has momentum, because the whole E equals mc squared. That's not the whole thing. You actually have like P plus PV and stuff like that. Because if a photon has momentum, which if they're talking about doing solar sails, and we're literally like catching the photons from solar energy, it's like, well, how does that work? Momentum. I mean, that kind of makes a sense to me. All right. Let's get back to something that I may actually be able to attempt to explain, rather than that deep philosophical question that I have not. If somebody else has an answer, please share it. Okay. So, as the general claim is, all right. So, if all of a sudden our universe, so to speak, was to be crammed down to a super dense point and everything, we became a black hole. Okay, there's some angular momentum, some rotation imparted to whatever structures are going to be going on, aka there would be a preferred direction. Now, again, these observations are of, what is it? This one, is it either 68 or maybe 148, maybe 263 galaxies? I forget. Hold on, let's see. It should say here, because I actually have the thing. How many galaxies did they do? Let's see. Boom. And here we go. Galaxies were 23. Okay. Direction were 23 of them in a row. Okay. Yeah, so we're 56 galaxies. That doesn't seem to be the largest sample size. So, number one, okay. Keep that in mind. Now, it's an interesting thing, because apparently, if you were to do a random sample, you would expect, but as the data goes up, maybe this will go away. Maybe we'll see more and more galaxies having angular momentum. Now, just because if there happen to be a preferred rotation of large scale structures, that does not necessarily mean we live in a black hole. And again, you could say, oh, why are they all going in the same direction? What might be going on here? I mean, I could totally speculate on that, and we will speculate. We're going to try to save that for the end. I'm going to try to stay within the bounds of generalized science and at least simple questions that may be asked. Maybe it's an inept question, but we're going to continue down that way. Okay. Because this is not the first time where people have talked about, oh, do we live inside a black hole? Why would we even say something like that? Okay. So the reason we would say something like that is because if we take, I believe it's, we can just, let's do this on the board. Why? Because I have a board, and I should actually practice doing these things rather than just being like, oh, look at my screen, look at my screen. Don't get me wrong. Feel free to trust, but just verify. Okay, so we'll leave. We can erase these for now. That's good. All right, so the whole thing is, if we take the what is it? The mass of its mass of, again, lower u, universe, and then we multiply it. How's this go again? Mass of universe, and then we divide it by, oh, like the radius. Mass divided by radius. Hold on. Okay, never mind. I don't know. Well, I think it's like mass times universe. So let's just do this before I start completely embarrassing myself more. Okay, so mass of universe. Oh, no. It's mass divided by volume. All right, so mass of universe. Mass of universe divided by volume of universe, or at least the observable. And the claim is that's approximately equal to a black hole. Wait a second, that doesn't make any sense. Black holes, they're supposed to be like really dense, super things, but it's like, how could we do that? It's like there is a 2-to-1 conversion factor for every Planck mass to the Planck radius, which is an interesting thing because mass of universe divided by volume of universe. Let's see. All right. Okay, so we get this number here. Okay, so let's do massive universe black hole. I think. All right. So if you take, here's the thing. All right. So where were we? All right. So basically, if you do, this is probably the easier way to just do it. So if you take the mass of the observable universe, we get an event horizon radius. So basically, if you were to have a center, where would the horizon radius be? It's about 10 to the 27 meters. Oh, that seems to be at least of the magnitude of the diameter of the observable universe. So diameter is 2 radius. So this is actually about 2.35. So it's pretty close to the actual radius of our observable universe. Okay. Event horizon area. Okay. So if we look at this, and again, you're getting that radius that's of the magnitude of our observable universe. Huh. That's that does seem to be a very interesting thing there. Because basically what happens is if we just do black hole, let's just do this. Here's the thing. Don't worry. You're going to see some things. All you got to know is 1 in, 2 out. That's the interesting quirk here. And maybe that's a formula. I'm trying to. Okay. All you got to know is this. This right here. It's 2 gm. That's just the Newtonian gravitational constant. That's mass. And that's the speed of light squared. That's the energy conversion factor. So if we literally do that, by literally, well, parentheses 2, Newtonian gravitational constant, and then we just throw in the Planck mass, and we just divide that by c squared. Boom. All right. So I get this number here. What is this? 2 Planck length. Okay. Since we got a 2 there, if we take out that 2, what happens? I wonder. Oh, look, we get 1 Planck length. But this is the Schwarzschild solution answer. This is supposed to be for a minimal, non-rotating black hole. The solution is for every Planck mass in, we get 2 of those out. It's oh, well, to be fair, it actually is 2 Planck mass in. Never mind. Uh, that just happens to be the solution. Okay, I stand corrected. Don't listen to the words coming out of my mouth. Commutivity! Math! Oh God, I had arranged something in my head about redoing the way I think about things or how I pronounce different units. Because I used to say like mass area rate, where it's like, well, it's actually an area. Mass is probably easier to think about. Oh God, I've missed. Oh, there's so much stuff going on. Let's see. Da, da, da. Yeah, heck. See, that's the interesting things. Apparently, the black holes are they're very good at dragging on things. Yeah. Let's see what we got. Greg is commenting. I've always wondered because C is meant to be a constant in a vacuum, except around black holes. I have questions. Well, to be fair, that's why they have to say speed of light in a vacuum. Now, that's when they say that the speed of light moves at the speed of light. Now, that actual velocity of the speed of light is going to depend because if it's in water, it does go slower. That's kind of like how we can detect neutrinos and stuff because it gives off Cherenkov radiation. Because the neutrinos basically going to still be going at the speed of light because it barely interacts with anything. It's zooming along at right about the speed of light, a little bit under because it's got some mass, we think, and then has an interaction, and then you're going to see that interaction kind of like a little bit of blue light and stuff. But around the black holes, that seems to be an effect of space-time itself, we believe. So it seems to be an effect of the medium itself, of that black hole, essentially. They call it almost frame dragging. And it's like, again, there's complicated stuff that goes in there, but I'm just like, wait a second. I play games online. I've lagged. I know what frame dragging's like. You're kind of going on and on. I played on a 28.8 modem. I remember some of those things. I've also gone far too fast on a motorcycle before, and it's like, oh yeah, those lines when they start to become one. I've made poor choices, so maybe I understand that. I don't know. Well, Bishop, when Sagittarius, basically, I forget. Sagittarius is a constellation. I think they're that collided. Oh, I don't know. I don't know about that actually. I thought you were going to talk about the Milky Way and Andromeda. So we'd have the delicious Milkdromeda galaxy because we can say that. Coriolis. Well, see, that's going to be an interesting thing because where would I think most of the stuff we have a lot of stuff in the southern hemisphere. My thought is where in the ecliptic and stuff. So basically, if you were to draw like a map out from Earth, a lot of observations we have are usually from like kind of one side because a lot of places telescopes are in Chile, the South Pole, and then like the southern United States and stuff. Actually drove by some. I think it was New Mexico or something like that when we were going down to Texas for the conference. There's a lot of interesting stuff there. But I mean, I have my own personal thoughts on that. But again, we're going to have to follow the data and we'll see where it leads us. Let me see. Bishop's commenting that from a standing point, everything in space is already going faster than the speed of light. That's why dialing a Stargate is such a pain. I watched some of that back in the day, and I remember it being fun, and that I just never got into it because I don't know, old school TV, and not if you miss one, then you're like, oh, okay. Let's see, how much mass is our sun losing? I think there's actually amount of radiation emitted. Hold on, energy emitted by sun per second. Please correct my spelling error. Let's see if Wolfram can do this. Convert. Oh God. Okay, it's good. Sun energy. There we go. Sun energy output. All right. 10 to the 26 watts. I think watts is Yeah, it's a per second calculation, so it's, let's see. Yeah, that's a lot. That's a lot of watts, my dude. Cool. All right, so we can get out of there. Let's see where else we got. Well, Hex is commenting about they tried to harness Coriolis forces with devices, but this is one of the craziest things that I heard Stephen Wolfram say. I'll bring up the video. Is that as far as like perpetual motion goes and stuff, it's like, what the heck is that? It's I think it's Sadiq Carnot, or he was one of the individuals that worked on like early thermodynamics for maximum engine efficiency and everything. And basically, there have been different Carnot machines or perpetual motion machines, like the first kind, the second kind, the third kind. Stephen Wolfram, at one point, he made a comment about, he wrote a paper on the thermodynamics of the vacuum with his collaborator, Jan Amjorn. And what apparently had happened, he did the paper, a few years went by, and then there was a physicist slash sci-fi author, Robert Ford, and he contacted me. He's like, "Are you sure your calculations are correct?" And he's like, "Yeah, I'm pretty sure my calculations are correct." He's like, "Well, if your calculations are correct, there must exist somewhere a basically a form of a Carnot machine of the second or third kind, basically some form of perpetual motion." And then Stephen Wolfram, his response to this, he's like, "Well, I look at what he said, and he was right." And I'm like, wait. Pause. Pause just a second. Did you just low key state that there must exist some form of perpetual motion configuration? Because what they found is utilizing, I believe it was a Casimir force or something. Basically, if you had a small enough box that you could squidge very precisely in different ways, you could actually make use of the vacuum fluctuations and essentially, more or less, quote unquote, mine energy from the vacuum. He did later say that probably couldn't do this utilizing normal matter, because what's the whole thing you're supposed to do with a Casimir effect is block certain wavelengths, and matter isn't completely opaque because it may or may not be bound light. Thank you, Kali. But well, that's one of those things where it's like, all right, you can't block everything with matter. Though he conjectured that I suspect you could do that with a field configuration, and I'm like, huh, that's very interesting. So let's see. Hold on. Let's bring that up. Let's see if we can't find that part.
Asks, has anyone ever done further investigation into the paper that I wrote long ago with my friend Jan Ambjorn on the thermodynamics of the vacuum? Yeah, well, so that was in 1981, I think. It was when I was still a card-carrying particle physicist, sort of. Wrote a couple of papers called Properties of the Vacuum, and there's one called Mechanical, one called Electrodynamic. And we promised a part 3, which was which was about gravitational properties of the vacuum. We never wrote part 3. We got many, many requests over the years for part 3. And I think I finally figured out a year or two ago what part 3 should talk about. But at the time, back in the beginning of the 1980s, was a time when gravitational properties of the vacuum were definitely things that were sort of emerging through studies of Hawking radiation, black holes, other kinds of things like this. But we didn't sort of know how that worked. I think we now do know how that works. And I keep on telling Jan Ambjorn that we should, I keep on saying, let's spend a weekend and try and write part 3. And I don't think he takes me seriously because, he's an academic, and academics don't write papers, substantial papers in a weekend. It's only crazy people like me who've spent decades building tools and so on, that it becomes even conceivable to actually do significant scientific work in a weekend.
So I just see, if there's one thing I've learned from the internet, there's a lot of us crazy people out there. Sometimes the question isn't, is this person crazy? It's, Are they crazy enough? I think I may have stumbled across a few of them. Actually, perhaps even on here.
But in any case, if you ask what became of those papers, the most interesting thing that became of them, they were studying kind of what happens to a little piece of vacuum that's put in a box. And actually, a chap called Robert Forward pointed out quite a few years after we'd written those papers, said, you know what, the way that you've set this up, there's been as you change the shape of this box. By the way, the big effect is a thing called the Casimir effect, which is that if you have two big metal plates, and they're very close together, and it's all in the vacuum, there's a small force of attraction between those metal plates. The origin of that is that in quantum field theory, there are always vacuum fluctuations. There are always 0-point fluctuations of the field, for example, the electromagnetic field. There's always little electron-positron pairs that are coming up and disappearing in short amounts of time. There are always these fluctuations in the electromagnetic field. But it turns out between the plates, the presence of those plates is cutting out certain low frequency, long wavelength fluctuations of the field. So there are fewer fluctuations of the field between the plates than there are outside the plates. And that's sort of why there's a force of attraction even in the vacuum between those plates, because sort of the vacuum isn't quite the same between the plates because you've cut out these low frequency modes by the fact that the plates are there. Well, that argument about, that sort of intuitive argument doesn't quite work, because if you have a metal box, so to speak, that's a whole three-dimensional box, actually the force, the Casimir effect, goes to be a pressure outwards rather than a pressure inwards. People for a little while thought that maybe the Casimir effect could account for kind of a mechanical model of the electron, where the electron will be sort of held together by Casimir forces, even though electrostatic forces would tend to make it fall apart. But it doesn't work, because the intuitive argument I gave isn't quite right when you analyze the three-dimensional modes of the electromagnetic field, which is what Jan and I did back in 1981. And we kind of analyzed it for arbitrary shapes of boxes. And what Robert Forward then pointed out was, if you take our results on these shapes of boxes, you kind of squidge them around, you will discover that there's a closed cycle, very much like Carnot's cycle, a closed cycle of action to this machine in the vacuum, so to speak. If you change the shape of this box.
Sorry, I slightly coded that box in reverse. It's the generalized concept is you have a volume, and as long as you can squidge and deform it in a very particular way, you're allowed to do that. And it basically doesn't, you're basically utilizing the energy of the vacuum to do the squidging and stuff for you. And then theoretically, as he's going to get into, Dr. Ford, he had proposed something like a vacuum fluctuation battery. And you're like, oh, that's a crazy idea. And then you see it was posted on Caltech's website, and you're like, crazy or sufficiently crazy? Continue, Professor.
In the vacuum, you can go through a closed cycle and extract energy from the vacuum. And so he wrote some papers. He was also a science fiction writer, and I think he put this in his science fiction books as well. But he wrote papers about kind of extracting energy from 0-point energy of the vacuum. And it even became, there were some studies of kind of spacecraft propulsion based on 0-point energy. I think the main place where that's landed is in dialogue in various science fiction movies about sort of 0-point energy as a source of action of various kinds. But in any case, that was so. It seemed, at first when this came up, it was like, did I get the calculations wrong? Well, no, I didn't. But the thing that happens, so does this work? Can you extract energy from the vacuum? Can you make a perpetual motion machine basically by using this closed cycle of these Casimir forces and so on? Well, the answer I think is no, because basically what happens is in that when you make these sort of borders and you're trying to sort of prevent vacuum, you're trying to constrain the vacuum. Turns out you can only do that to some extent. It turns out that it's only opaque to some modes, but in order to make this work, it has to be the case that this material is sort of perfectly opaque. And by the time it starts to be affected by the fact that you have to make the material out of atoms and so on, and you can't make something which sort of has that perfect opacity. You might wonder, could you make a configuration?
Now, again, when doing videos on the internet, as I had originally started off as primarily a troll, and I am still a troll and everything as well. A lot of it was just like, so I could just harvest clips about people saying maybe silly things. Like,
turtles all the way down.
But life is a heck of a ride. That's the thing. It's, if there's one thing that I could take away from Wolfram, the whole concept of computational reducibility, it's like, so what you're saying is the game must be played. That's what I'm hearing. I mean, I totally stole that phrase from Harry Potter and the Half-Blood Prince when Harry's going on his adventure with Dumbledore and they go into the cave to grab the Horcrux. And Dumbledore's like, it must be drunk. And he goes through, it's so terrible and everything. But I'm like, so the game must be played. And for some people, it ain't a pleasant game. I think that's something we should probably acknowledge, not pretend like it doesn't exist, because, yeah, first step to fixing any problem is acknowledging we have one. Back to theoretical science, my friends. Okay, so the reason why I was saying that is because I was going over these things, and I remember he said something, but then he gets to the point where he's like, "Oh, I suspect you can't do that." Who includes a fairly notable scientist saying they suspect you couldn't do this? Well, I mean, if you're trying to do science, you're trying to look for truth or to be closer to truth. Shout out to Robert Lawrence Kuhn. Hope you're all right. When you look at this, it's like, all right, let's get somebody's full statement, because we all know nobody would ever take something out of context on the internet. My personal opinion is, if you actually have confidence in what you're saying, you're willing to listen to the things that don't necessarily support you, because, well, if everyone's just around nodding, going, "Oh, yes, strong. Oh, good job. Good job." If they're just saying the things you want to hear, there's a difference between that and saying what you need to hear. That said, you don't have to be a dick. You can choose to. I ain't anybody's mom, but let's go back to, so basically he suspects the whole thing is to do some form of perpetual motion. If you want to do that, you're going to have to need some perfect optimal opacity. And the problem with matter is you can only block so many wavelengths and stuff. So now he's going to get into a potential field configuration.
Be affected by the fact that you have to make the material out of atoms and so on, and you can't make something which sort of has that perfect opacity. You might wonder, could you make a configuration of a field, just like when you do plasma confinement in a to get fusion, you're not trying to constrain that 10 million degree plasma in a, no material substance can have its atoms hang together at 10 million degrees, but a magnetic field doesn't care about temperature in that sense. And so you can have a magnetic field that can withstand that. And it makes me wonder, as I'm thinking about this now, whether you can imagine kind of a field that is constructed to make sort of this box that will constrain the vacuum. It's worth looking at, actually. Worth looking at. It's kind of that would be the ultimate irony if on the 200th anniversary of Carnot's argument that there can, where he used the argument that there can be no perpetual motion machine, if in fact one figures out how to construct a perpetual motion machine that it continually extracts energy from the vacuum.
Now, I'm just saying, to be fair, when I clipped that off, he said it's not an impossible thing, but who cares? I just realized I erased everything behind me. All right. Now, the reason I'm very biased to this, and this is a bit of a tangent there, is now, if it were hypothetically possible, if there was a very particular field configuration that could allow for, let's say, essentially perpetual motion. I'm sure there's a very rigorous definition that I'm not hitting there, but if there was a form of something to persist, what might that be? See, that was a crazy thing. I listened to Thad. You have that whole model and everything, and it's like, all right, if I took this seriously, what he was saying, what would happen? And then all of a sudden I hear Professor Wolfram say at one point, it's like, I suspect you could do it with a field configuration. And the sheer fact, he's like, I looked at the calculation and he was right. I'm like, wait, you said that very casually. And it kind of stuck with me a little bit. But all right, back to black holes. All right. So number one, if we happen to live inside a black hole, that might explain a lot, because when you're taking the amount of mass in the observable universe and everything, and then you're looking at the radius of the observable universe, it's like, well, if we took all that mass and it wasn't a black hole, it would be about the radius of our observable universe. It's like, well, that's interesting. Seems to be a coincidence there. Hey, Tommy, what's going on, my friend? The Guinea Pig Collective stomping through, checking out some old action figures. I actually showed one of my friend's sons your channel the other day because he was big into Spawn. And I'm like, oh yeah, check out some of Vinny's artwork, because I told him that you have Vinny on, and Vinny had done some of, like, was it? He did the medieval Spawn, or somebody's like, what? It's like, yeah, no, hey, feel free to check it out. But very cool. But no, we're talking about black holes. Why? Because it's a Black Hole Friday. So basically, this whole thing behind me is essentially, if you take the mass of universe and you take the volume of universe, again, lowercase u for our observable universe, it, to a pretty good approximation, is about the density of a black hole of this size. So that gets you going, and you're like, well, that's interesting. And then it's like, you see that, and it's like, all right, well, what if we were to account for more? And this happens to either be a problem, a solution, or a very interesting thing, because even within the model that Thad basically said that, all right, if you're going to have a minimum length, you would have a maximum length. And then that basically happens to be part of what's in physics that I learned recently, the concept of maximum extendability. You would have some logical process, because when you hear folks saying that, well, the universe is infinite as far as we know. Okay, how do they get that? Well, if you think you can continue to get smaller and smaller and smaller infinitely, well, then the inverse of that would be infinity. So if you go down infinitely small, you're going to get infinitely big. Okay. But at least, according to physics as we know it, there is a minimum of length, the Planck length, 10 to the minus 35 meters. What the heck is that? All right, so basically take the entire observable universe, and I think it's like a grain of sand on the Earth. It's something ridiculous. But the thing is, there's that minimum. So if there was a minimum, well, shouldn't there be a maximum? That if you do that calculation, there is a maximum. It's freaking ginormous. How do you do that calculation? It must be so complicated. You have to study for years. Or you literally just do this. You do Planck length. And this is a very small unit. This is a unit of length, and it's expressed in meters. That's a unit of length. You can do it in feet if you want, but the whole point of SI, or the metric system, is to have a coherent system of units. It also happened to help with that when it started off. It was literally defined by water. And that, like, was it a cubic meter of water? It's like 1,000 kilograms. And then it's, yeah, we basically originally the metric system was based off of that. Or I think it was after they went from like 1 million paces from France to the North Pole. There's some real crazy stories within history. So a minimum length. All right. So what if we did something silly and we do the inverse of that? All right. Just 1 over. That's a really big number. But the problem is it's in reciprocal meters. We don't want that. So this unit is in meters. So what if we just did meters? Because meters is the one of reference. All right, we get the same number out, but with no dimensions. Why? This is just a physical dimension of measure, to our knowledge, of a length divided by a length, which cancels out the units. Okay. So if we do the naive thing and we literally just square meters, so we've got 2 units of length divided by 1 unit of length. Okay. So all it does is for this 2, we cancel out the dimension of 1 there. So we get 1. So basically the claim is the radius of universe is, that's roughly about 100 million times larger than what we see. Not infinity, but frickin' ginormous. Okay. So the whole reason I showed you that is if you do a little naive calculation, let's say, let's change this up a bit. Let's go to a dimensionless number. So we'll have the same magnitude, but we're going to square this. And we're going to set it equal to, I don't know, let's solve for x in kilograms, and let's divide it by, we had the Planck length over here, so let's do the Planck mass over here. Because we can. And we let the magical oracle that is Wolfram Alpha do the calculation for us. Yeah. He gives us a little graph, gives us some numbers, solves for x. Oh my God. What is this abomination right here? So we were solving for kilograms. So 2 to the 128. How cool. That's what happens when you're a numerologist. So we're going to slap kilograms on it because that was the x we were solving for. I know. We're back to... This was stuff in high school where I'm just like, I just didn't retain. I was lost. All right. So just so you know, okay. 10 to the 64 grams. If we do kilograms, it's 61. So for my sake and memory, this is how I know it. Kilograms. Okay. So this is an estimate of the, let's say, mass bank of universe, so to speak. Or at least I'm willing to postulate that claim. Happy to be corrected. So as we can see, about, again, 10 to the 8 is a 100 million times the mass of the ordinary matter in our universe. Literally, it's what? No. Maria, here's the thing. I think you can appreciate this. You want to know what I did? Okay. I was pretty good until I got halfway through the 6th grade. Halfway through the 6th grade in math class, our teacher said, you don't need to know this now, but it'll be useful later. She then taught us how to cross multiply fractions. Then moved on to the 7th grade. And it was like, so now that you know how to cross multiply fraction, here are letters. And then I just the system probably just moved me along realistically. But when I say this, it's, listen, I'm not a PhD physicist. I'm not a mathematician. I'm a dude on the internet like a lot of y'all that happens to have interest in the way our world and realm of persistence, our universe, so to speak, is, because, well, we're here and we seem to be able to have some agency and stuff. So let's do the best we can. Ultimately, I don't know any better. I'm literally just working with what seems interesting to me. It probably also doesn't hurt that I may or may not have been taught and listened to lectures and had conversations with some individuals who I believe are sufficiently crazy that may have noticed some very deeply hidden things, maybe not so hidden, but it takes a certain perspective and position in life, because I think a lot of what Dick Feynman said, Professor Feynman, won like Nobel Prize and stuff, a lot of folks learned physics from him. The Feynman lectures and the bongo dude. A lot of stuff that he said, he's like, I was in the right place at the right time. And you listen to some of it and, oh man, he came up. Okay, let's end with some Feynman because that's fun. All right, let's get ourselves a copy strike with some music. All right, so Feynman. Huh? This one. All right, bring that up. Close this. Shoop. All right, let's see. Okay, this is a fun one. So this is what I claim is Richard Feynman's most fantastic moment. It's a heck of a story.
So I came back in a month or so, and Stone and Webster Company engineers had finished designing the plant, and now it was for me to look at the plant, okay? How do you look at a plant that ain't built yet? I don't know. So I go into this room with these fellas, take me into the room. There was always a Lieutenant Zumwalt that was always coming around with me, taking care of me. You know, I had to have an escort everywhere. So he goes with me, takes me into this room, and there are these two engineers and a long table, great big long table, tremendous thing, covered with a blueprint that's as big as a table. Not one blueprint, but a stack of blueprints like this. I took mechanical drawing when I was in school, but I wasn't too good at reading blueprints. So they start to explain it to me because they thought I was a genius. And they start out, Mr. Pryor, we'd like you to understand, the plant is so designed. You see, one of the things we had to avoid was accumulation. Problems like there's an evaporator working, which is trying to accumulate the stuff. If the valve gets stuck or something like that and accumulate too much stuff, it'll explode. So they explained to me that this plant is designed so that no one valve, if any one valve gets stuck, nothing will happen. It needs at least two valves everywhere. So that is explaining how it works.
So, okay, they're laying it out. They're laying out the scenes and everything about what's going on. And as far as they know, he was sent there by Oppenheimer and everything to make sure that things were safe. Here's the thing you need to know. At that time, he was a young man, hadn't completed his degree and everything, was working on some top secret project for the United States government, and now he's in there with a whole bunch of engineers, and he's responsible for making this plant safe. Okay. Oh, yeah, and they also thought he was a genius because he wanted to make them think he was smart. So as they were going around the plant, he memorized one of the building and vat numbers, so he repeated it back the next morning specifically. That may have been one of the few things he really actually remembered, but as soon as he spit it out, they're like, whoa. They thought he knew they thought he was a genius. So since they think he's a genius, they treat him like a genius, and he's going to know everything, even if he doesn't. Keep that in mind.
The carbon tetrachloride comes in here, the uranium nitrate from here comes in here, it goes up and down, it goes through the floor, comes up through the pipes, coming up from the second floor, through the blueprints, down, up, down, up. Very fast talking, explaining it. Very complicated chemical plant. I'm completely dazed. Worse, I don't know what the symbols on the blueprint mean. There's some kind of a thing that at first I think it's a window. It's a square with a little cross in the middle like this, all over the damn place. Lines with this damn square, lines with this damn square. I think it's a window. No, it can't be a window because it ain't always at the edge. I want to ask him what it is. Now, you must have been in a situation like this. You didn't ask him right away. Right away it would have been okay. But they've been talking a little bit too long. You hesitated too long. If you ask them now, they'll say, what are you wasting my time all this time for? I don't know what to do. I think to myself, I swear, often in my life I've been lucky. You are not going to believe this story, but I swear it's absolutely true. It's such sensational luck. I think, what am I going to do? What am I going to do? I got an idea. Maybe it's a valve. So in order to find out whether it's a valve or not, I take my finger and I put it down in the middle of one of the blueprints on page number 3 down in the end. I say, what happens if this valve gets stuck? Figuring they're going to say that's not a valve, so that's a window. So one looks at the other and says, well, if that valve gets stuck, and they go up and down in the blueprint, up and down the blueprint, or they're going up and down the blueprint, back and forth, back and forth, back and forth. They both look at each other and they chick, 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 and they turn around to me and they open them out like this. You're absolutely right, sir.
So just for reference, when I first listened to the Los Alamos from Below lectures from Professor Feynman, as it starts out, the crowd is laughing. I'm like, all right, this reminds me of a Robin Williams like live on Broadway bit, except it's science. So at one point I asked Wolfram if Dick Feynman could have made it as a stand-up comedian, which he's like, I have no idea. I'm not really qualified. That was ultimately what he said, more or less. Let's wrap up. So
they rolled up the blueprints of the way they went, and we walked out. And Mr. Zumwalt, who'd been following me all the way through, he says, you're a genius. He said, I got the idea you're a genius when you went through the plant once and you could tell them about evaporator C21 and build 9207 the next morning. He says, and when you knew all about the neutron regime, but what you have just done, he said, was so fantastic. I want to know how. How do you do something like that? I told him, you try to find out whether it's a valve or not.
Because that. See, I love that story because a lot of folks, you'll see a lot of like these smart people, and we hold them in such high regard. And I think back, I'm like, weren't there a lot of old stories telling us to be wary of idolatry or something like that? But I mean, hey, we're human beings. We like doing that. Just having a story from somebody that happens to be one of the most famous scientists, for better or worse, whatever you believe there, well-known name, very famous, that literally, as he went through, people thought he was a genius. It's like, no, I'm literally trying to get by and helping to have these people trust me so they would actually listen to what this kid was going to say. I thought that was a cool story because I think a lot of it also comes down to luck and stuff. Because, I mean, you could be literally the smartest person in the world, but if you don't have like your next meal or shelter or stuff like that, it's kind of hard to put your genius to use sometimes. That's a different story for another time, but it's getting a little bit late. We've gone over for an hour. But to answer Greg's question there, one of the things is I kind of started getting into this when people were talking about theories of everything. So I'm like, whoa, this seems cool. If we're getting there, can string theory thread the needle? Does this particular argument hold water? It's a fascinating thing. And then I go through and trying to learn. And then when it gets to the point where it's like, okay, if you're going to say everything, personally, I'm kind of more in the Wolfram camp in that I'm looking for a fundamental theory of physics. That's primarily, if you're going to say everything and you try to wrap up conscious, that seems complicated. I'll let the smarter folks deal with that and everything. That's why a lot of these things are a bit more targeted, where it's like, all right, so before one tries to solve for everything, maybe we should try to figure out one thing. And maybe that one thing will lead to another and lead to a few more other things. And I don't know, is that how the dominoes fall? Is that how they get kicked back up? How does it even work? I don't know. But hey, thank you all for joining. We had a very eclectic crowd in here. We've got Maria, we've got Jason, we got Jax, we got Greg, we've got Rick, we've got Tommy, we got David, Kale. Oh wow, Hex, bunch of the crew here. I think I may have seen a few new people, so that's pretty cool. Yes, Rick, it is that time. You are correct. So with that, my friends, take care of yourselves. Peace out, everybody. I should be traveling for most of next week, going back to the monastery and stuff, and maybe Vegas because WrestleMania. But other than that, y'all take care. Stay safe, everyone.